Hello everyone, good afternoon. So I request everyone to join in fast. So we have to start the session in a couple of minutes, and most probably in 5 minutes we're going to start. So I request all my dear faculty members, students, colleagues, and professors. So please join in fast so we can start the session. I'm going to start again from the beginning, we'll try to understand the entire operations like most of us have requested. And we'll try to understand using the one example, and we'll go ahead and try to understand the entire mathematics, and then we'll try to implement one project. All right. So guys, hurry up, please. I request all the professors, colleagues, team members, dear faculty members to join in fast so we can start the session and we can start the discussion. All right. So good afternoon once again, and hope to see you fast. Okay. So please join in fast, guys. So humble request to everyone so we can start the session in 5 minutes. Yeah, guys, I request everyone to join in fast. So yesterday's session, hope you guys have found it very interesting. Today also we'll try to make effort. So today's session we'll also try to make it very interesting. We'll try to recap again all the things, whatever things we have learned yesterday. I will try to understand the entire forward propagation mathematics once again, and then we'll start with the back propagation, guys. And once we complete this, we'll try to include the live example, one for the image data and one for the structured data. So hope you guys are excited. for the today's session. So you guys can give me a thumbs up, give me confirmation, so we can start in 2 minutes, guys. So you can start interacting. Meanwhile, you can start asking questions. You can start raising your queries and all. I will try to take it simultaneously, everyone. So please ping me, guys, in the chat box if you have any questions, any suggestions, and we can start in 2 minutes. I hope we have crossed already to 230 plus, and I hope to see a couple of hundreds of more people joining in fast. So I request everyone to cooperate and please join in fast so we can start the session. And we don't worry, guys. Whosoever yesterday felt that I went a bit fast, so I'll try to recap again all the things. All right. Okay. Let's see what else you guys are saying. So guys, last 2 minutes and we'll start the session. Yes, sir. Thanks for asking, Prakash Kumar, sir. Thanks for the question. So, yes, how to create own tool as ChatGPT? Yes, sir. I would like to tell you this. Maybe on the last day, I will try to cover this ChatGPT kind of a tool topic. So, if the time permits, and I would request APSSD and other professor and colleague members, if you are really interested in this kind of a generative AI technology and tools, so we should arrange one more separate session for this one because this chat GPT is not that simple architecture. We need to understand the entire transformer architecture first, which is the advanced version of the recurrent neural network. And then maybe we try to build up one kind of application just like the chat GPT. So at that time, it is also a paid kind of a subscription, guys. So if you want to create this kind of a tool, you have to use the LangChain and the OpenAI tools. So it's a kind of a paid. I'll try to see if I can arrange some open free source tool. So where we can utilize this entire functionality. So I'll keep in mind. Thank you for bringing this, Prakash Kumar. Thank you. I'll try to include. I'll try to include something, or we'll try to include at least some kind of a chatbot using GPT-2 or whichever the free version is there. All right. So guys, hope everyone is joined in now. So we can start without wasting much of the time on today's session. And let's get started once again, back from the beginning. And we'll try to recap like what we were able to understand yesterday. And we'll try to compare the entire functionality of the human brain functionality. We'll try to recap it fast. And then we'll try to understand very, very slowly in phased-wise manner how the ANN works upon and what are the calculations which are happening. What do you mean by forward propagation? What do you mean by backward propagation? And what are activation function, loss function, optimizers, everything we'll try to uncover today very slowly in a phase wise manner. I will go and in yes I will write a neat and clean. I'll try to include the separate slides for everything. All right. So guys, hope everyone is now excited to start, and just give me kind of one more confirmation, give me thumbs up, give me a kind of a go ahead, and we can start, guys. I think we have reached to 60 plus, so other people might be joining fast. We can start with the recap then. Right. So guys, everyone able to view my screen and I am clearly audible and visible as well. So it's 40% from the participant sides. Please anyone confirm so I can start. All right, Prakash Kumar sir, thank you. So we can start now. So, okay. So guys, yesterday we started something understanding about the neural networks, and we wanted to understand like how the human functionality works upon, and on the basis of the human functionality, guys, human brain functionality, obviously, we wanted to understand how the entire artificial neural networks are adopted. All right. Thank you, sir. Prakash BS. Thank you. Thanks for confirmation. So guys, let's get started without wasting much of your time. So let's try to compare once again. What I'm going to do is, this is human brain and this is artificial neural network. Okay, ANN, popularly called as ANN. So what we started with the discussion that going forward, the illiterate of the century will be not be the one who cannot read and write, but one who will not be able to understand the AI, guys. And this is gonna be true. Trust me. And looking at the trend, looking at the technology, looking at the entire technological development, nowadays AI will become a new normal. Okay, AI will become new normal, just like everything is now internet enabled and everything is now based on the internet. Likewise, everything will be based on the AI, guys, going forward. Let it be a banking, let it be agriculture, let it be our everyday life, let it be a corporate, let it be education, let it be everything. All right. So, especially for the professor, today I just was going through one of my LinkedIn community, and what I found a beautiful quote. Actually, I will try to include that picture for tomorrow. And that quote was in such a way that people are now fearing, when this generative AI has been introduced, people are fearing that all our professors and institutions will be replaced by the AI, right? This is what the fear was among the people. And very, very beautiful quote which has been put up, and that kind of a meme was there. And what that guy said is not the professor chat GPT. Okay, they're specially talking about this chat GPT. Not the chat GPT will replace, but the people who are not aware of the chat GPT will be replaced. Okay. Or they wanted to showcase in such a way that people who are not aware of the application, just like the generative AI, will be replaced. So in short, if I try to conclude, it is very beautiful picture, guys. I'll try to include that. And in short, they are saying that one who are not aware of the AI will be getting replaced nowadays. And let it be not only institution, but guys in corporates as well. Nowadays, writing code will not be a necessity going forward. So code can be generated automatically by the application, just like the chat GPT. What you have to do is you have to analyze the code, you have to architect the things, and all the repetitive job will be ended, guys. And that's for sure in upcoming decade, this is gonna be true. So it is better that we try to prepare us. So job will not be taken away, but the way job will be done will be refined, guys. All right. So hope you find this quote very useful, and let's get started again. Try to understand our ANN and try to compare with the human brain neural network, HBN, human biological neural networks. Okay. So if I try to take this, just a recap, guys, so we can collect all the information, whatever things we have learned. So when I try to look at one neuron and I try to expand here, and this is what it looks like. And when I am trying to talk about this kind of a neuron, guys, so what I realized that neuron, or this human biological neural system, all right. So this works in a such a way that, so if I try to expand here, this will be called as our cell body. So this cell body is an entire CPU kind of a processing unit which conclude the nucleus. And this nucleus is trying to accept the information, try to process the information. And this is getting connected by this kind of a threads and this kind of a veins. And these veins are nothing but the dendroids. Dendroids become an input for us, and through the sensory organ like nose, mouth, eye, ear, and all the things, touch and feel, and we are able to take the senses and use these sensory organs and to try to take the inputs. And when the input is getting inside this dendroid, and dendroid will be carrying this throughout our body towards the cells, neurons in the human biological neural system. And then this will be called nothing called as in signals. And once we receive the signal, guys, along with the signal, we'll try to associate some kind of a weightages to the signal, and based on the criticality, based on the importance of the information, we'll decide whether to fire or not to fire the signal. And if the entire neuron decided that this information is critical, it will try to fire that information by showcasing some kind of a lightning out here. So this entire neuron will be get activated, and it by activation means it will try to glow this way, and it will try to create one kind of an electric spark out here. And by creating that spark, it will try to fire that signal. Signal is nothing but information we are talking about. So it is all about the triggering the information. So whether it will be able to trigger or not trigger. And based on that, guys, information will be passed on to the other human body parts or to the next layers and towards the end function, where we will be able to take the actions accordingly based on the signals we are receiving. So this is what the entire thing is all about. And when we try to receive the output, so it is through the axons. And axons have a terminus like this way. They have connected to each other, and they're trying to carry the information out. This is what we were able to understand yesterday, right? So what we decided is that we, as a human being, we decided in back in 1940s also, you've seen the gentleman Mackillop and Pitts. They made efforts. They made efforts to imitate the same human brain biological neural system. and they called something called as single perceptron model, single neuron model they created, and we were able to see what is the single neuron model. So let's try to compare that neuron with our artificial neuron, which is called as perceptron, right? Which is called as perceptron, and this perceptron is nothing but a copy of a biological neuron. And when we try to compare here, so what is going to happen is we are receiving the inputs just like from the dendroids. We are passing our inputs x1, x2, and x3. And what was happening is entire processing which was happening inside the neuron, which is called as perceptron here. So perceptron is able to sum up the information, whatever the signals, just the way signals, it is kind of a information input, you can say, right? Inputs. So we are passing the inputs, and it is trying to perform the summation of the inputs. And after summation of the inputs, let's say, let's call this as a capital X now. So let me rub these things and write it correctly, so there will not be any confusion. So when I'm passing this kind of inputs, right, let's call this inputs as x1, small x1, small x2, and small x3. What is happening is inside this perceptron, which is also a neuron, copy of a neuron, what I'm going to do is I'm going to sum up. You can see here summation sign. So I'm trying to sum up the information, and I'm calling it as a capital X. And what is happening is we are trying to associate some kind of a weightages out here, W, and then on the basis of this summation of the weight, this is what the single neuron model was doing. Single neuron model or single perceptron model, which was first introduced by the gentleman, by the statistician Mackelo and Pitts, and they made an effort back in 1941 also to imitate the entire human brain functionality, how we can copy it, and they try to put it artificially. That's why it was called as artificial neural networks. All right. Then what they decided is that the only functionality which will be done out here in the processing will be, we'll accumulate our results, we'll accumulate our inputs, the inputs just like the dendrites, we are passing the inputs, just like the nucleus, we have a new perceptron, which will be able to perform the action, which will be able to process the information. And once we process the information through the axon, we are passing the output through the axon terminal. Same way, will receive a output here, which is also called as our prediction y hat. All right. So the only job which was done by this entire neuron was just to trigger the information. Okay, just to trigger the information. Trigger means just decide whether to fire the signal or not to fire the signal. Okay, not to fire the signal, not to fire or fire means whether to pass on that information to the next layer or not, towards the next thing. Okay, so that is what the only functionality they tested, and they found out that this kind of a neural network or single neuron will not be useful. And later on they decided that we have to do something around it. So because the single neuron will not be effective, and they gave a birth to this kind of a network, which was called as multi-layer perceptron. Multi-layer perceptron. Multi-layer perceptron was the first model which was introduced, which was called as artificial neural network. So let's move to our next slide. Let's try to understand then how this entire multi-layer perceptron worked upon, what job it did, and how it looked like, right? I'll cover back this later on, guys. That this is the entire roadmap. If you want to become an entire AI expert, so this is the roadmap. I'll discuss this thing later on. So we'll today try to focus on the neural networks, artificial neural network. Then we'll try to understand the entire mathematics, and we'll try to understand the back propagation as well. So guys, let's start out here. So what you are able to see out here is something called as now the multi-layer perceptron. This is how the entire artificial neural network looks like. So it will have a 3-layer architecture. The first layer will be our input layer. So we call that as the input layer, and this is what the input layer is all about. So here what we are doing is, rather than taking the single neuron, single perceptron, you can call this as, so we are trying to arrange them in a stack-wise manner. So one above another, we have arranged it, and we'll try to understand going forward that whenever we try to create our own architecture of this kind of artificial neural network, so what kind of a neurons I should be taking, how many neurons I should be taking, how many layers I should be building, and what the entire architecture look like, and how we should be building the one, how we should be developing the one. We'll try to understand that one. All right. So the first architecture level, when I'm trying to discover this architecture, the first layer called is as input layer, which is just responsible to pass on the information, to hold on the information which has been passed out. So if we have a data, and this data has been passed on row wise manner, okay, one by one, and all this information will be hold upon in this layer, which is called as input layer. And once we have this input layer, guys, then we can see that when we trying to go or move towards the further towards the hidden layer, which is the second architecture, which is called as hidden layer. So it is also nothing but one kind of a stacking of the neural networks, perceptrons. So this perceptron again stacked above each other, and they are also having some kind of a connection with each other. So every neuron in the input layer, okay, this is neuron number one, I can say N1. So N1 is having a connection with the next layer and also with the second neuron, third neuron, everywhere. That is why you can see this kind of a black lines, entire kind of a architecture, entire kind of a entire connection. So this connection we understood are nothing but a called as weights. This connection are nothing but these thin lines are called as weights actually. So this these are connected by the weights, and then once the information is received, it will be passed on along with the multiplication by the weights, which we'll try to understand in the next slide, guys. So just I wanted to discuss this architecture. This is the input layer where it will be able to hold the information which has been passed. Let it be a structured data, let it be unstructured data, and then the entire processing will be done in the hidden layer. It is responsible to perform the processing. So we'll uncover all our two-step process, which we have discussed yesterday. We'll again try to uncover, we'll try to write the formulas. Okay, we'll try to understand what is happening. And then guys, hidden layer could be one layer, could be two layer, could be multiple layer, up to n layers. It could be possible, but it's so we need to carefully design this kind of a layering system, because whatever layers will be creating, that many weightages will be created, that many parameters will be created, right? And then when I talk about input, and once the input is hold on into these neurons, these are connected by this kind of a thin line. Every neuron is connected with every other neuron in the next layer, and with multiple connections, right? And this hidden layer also, they have a connection out here with the multiple neurons, and then the processing will happen in the inside every neuron. Every input will be gone into every neuron. That neuron will produce some output, which will be passed on to the next one. And then guys, after processing happens in the hidden layer, will generate one output, which is like here O, and that output will again get multiplied by one more weightages, and then in the end will receive a y hat, which is our prediction. All right. So this is what the architecture is all about, guys. So in short, if I want to summarize the artificial neural network, so artificial neural network is nothing but it is a copy of the human nervous system, or biological neuron system, which receiving, processing, and transmitting the information, which happens for receiving, processing, and transmitting the information. All right. So this is what I can say, and it is a copy of biological neural system. And how the entire architecture look like? Three-tier architecture. Okay, three-tier architecture divided into three tier. One is input, then hidden layer, and then the output layer. Just like this one: input, hidden, and the output layer. End of the output layer, you will receive your output prediction, what you are looking for. All right. So now I think we are having a very good understanding how the neural network looks upon, and what are the three stages or three layers which are broadly present in the neural network. And number of layers could be possible, that we can have up to n number of layers. There is no restriction. But one thing is very, very important, guys. Let me rub these things. All right. One thing is important, that the whatever input layer will be there, IP layer, there will be only one IP layer. So the output layer, which is the third part here, which will be also one layer, but which will be only one layer. But in between, whatever the hidden layers we are taking, their hidden layer can start from 1, and it can go up to n, guys. It can go up to n. So this is possible, and I have seen in reality that we have developed something called as right from beginning to 6 layer, to then 10 layers, to 30 layers, to 25 layers, to 50 layers, to 100 layers, to 150 layers, or 250 layers. This kind of a models are available, and I have worked with this kind of a models. These are really huge model, and these are a pre-trained model which are available, because to train this kind of layers, 250 plus layers, it will take a month's time. And also depend on the data, like what kind of a data you are providing. If you are providing a huge data kind of image data set, so let's imagine the data set which will be providing, like for one category of the data. Okay, one category of data, people try to take up to 10,000 images. Okay, so which I'll try to showcase you when we try to build our own architecture. So that is why before we try to begin and try to build this kind of a deep neural network, We have to think about the processing, we have to think about the computation power, and all the basis of that, all the equation we try to sum up here, we'll try to decide how our architecture look like based on the condition, based on the business logic. All right. So hope everyone is now very well clear what is happening here, what is ANN, and what are the different architecture available, what are the three layers, and majorly these are the three layers. There will be only single input layer, output layer will also be single, but in between hidden layer can be multiple layers. All right. So this is what we have understood, and this we already spoken about what McCulloch-Pitts neuron model did, and which was completely a failure, but it was a very good effort to make the artificial neural network copy, and then they gave up birth to this kind of a multi-layer perceptron model, guys. Okay. So this is nothing but a multi-layer perceptron model which we spoke about. So this is the same thing: input layer, hidden layer, and the output layer, and we'll be passing the information. It will go inside here. It will perform a two-step process. Step 1 and step 2. Two-step process will be happening with the help of the activation function. So we'll try to introduce today about the activation function. We'll try to introduce our entire optimizers today. We'll try to speak about our loss functions. And then in the end, we'll try to understand the dropout layers, which is the regularization technique dropout layer. All right. So let's get started with this one. So let's try to understand the entire working of this neural networks. For that reason, now what I'm going to do on this slide, guys, on this slide, I'll try to make you understand. So what kind of a business case we are going to solve. So my entire data will be looking this one. So let me draw my data, very simple data out here. So this is my structured data. I'm going to pass my structured data to my neural network. And by taking this same yesterday's example, we try to understand. My objective here is to create a BMI, a body mass index. Okay, a body mass index. This is very good index which gives us the bone density, entire entire bone density which is present inside my body. What is my fat percentage? What is my muscle percentage? All this kind of important information is provided by using this kind of index, body mass index. And on the basis of the BMI, nowadays people are trying to gauge whether you are a fit person, whether you are a obese person, okay, or whether you are a kind of a fat person. So this categorization has been mostly done, and nowadays everyone is very aware and various conscious about the health. So this is very good indicator, body mass index. All right. So let's try to predict this body mass index. We already know the formula, like weight divided by height square, and there are certain other formulas also. People try to take the divided by some kind of a fixed number, and they also try to divide using that formula. They try to derive the BMI number. Now my job out here to derive the BMI, which is my target here. So I am going to write my last column here, which is going to be a BMI here. So that will be called as Y, column Y. So this will become my target actually. This is my target, and this is what I am trying to predict. And my other columns here. So what I am writing here, my other columns is age column. I am writing age here. Then I am writing W for weight. Then I am passing my height H here. And then I will be passing my gender G here. And basis of height, weight, gender, and my age, guys, I will try to predict my BMI. All right. So this is the use case we are going to solve, and we'll try to understand in terms like how the neural network will work upon, what kind of a processing will be done. So guys, when I talk about artificial neural network, it will be trying to create this kind of a function out here. Entire my model will be called as y equal to wx plus b. Wx plus b. So when I try to talk about y is nothing my target, guys. Y is my target here. So then x is my input here. So x is not one single x. X will be x1, this age, x2 weight, x3 height, and my gender. Okay, all of this will be denoted by capital X. And then guys, these terms actually, which we talks about here, the W is nothing but called as weightages, which is unknown to us in this equation, weights. And this is something called as B, which is our bias, which is called as bias. Okay, B stands for bias, and bias and the weights. Let me show it to you with the different color now. So these are unknown to me as of now, unknown I am writing. And what is known to me is this X actually. X is my input, this X. All these four columns will be called as my X. This is what I will be passing, and I am supposed to achieve Y using this kind of a formula, which is Y equal to WX plus B. All right, guys, this is what I am going to showcase. This is what we are to solve here. So what I am trying to do is I am created this kind of a neural network here, which has only one hidden layer, hidden one, which has only output layer here, OL, and which has an input layer here. All right. So what I'm going to do is I'm going to pass. Yes, I will try to make a new slide, guys, for calculation. For this slide, I'm just putting the information here. So what the use case I'm going to solve and what neural network I created. All right. So here I will be passing my age here, age as x1. I will be passing my height here as x2. I will be passing my weight here, which is x3. I will be passing my gender here, which will be x4. All right. So you guys can see that this input layers are now connected by this kind of a thin lines. The thin lines are nothing but our weights, right? So I am calling this as weight 1, this as weight 2, this as weight 3, and this as weight 4. All right. So this in between there are weights, and there is also weight 5 here. So we could be weight 6 here, and this could be weight 7 here. And in the end, maybe we'll have some kind of a last output layer. So output layer I will not call as this, I will call as hidden layer 2 again. Hidden layer 2. And after W7, let's call this as W8 here. The last weightages which will get multiplied. And here out of this output layer here, OP, I will be getting my Y hat, guys. Okay. So this is what going to happen here now. All right. So everyone aware, everyone comfortable now, what is going to happen, what kind of a use case we are solving here. And by using this use case, we'll try to understand. Now what I'm trying to do is, I'm passing my age x1, I'm passing my height x2, I'm passing my weight x3, I'm passing my gender x4. Now what will happen now? Let me change the color now. All right. So what is going to happen is, when I'm passing this input layer, just will be able to hold the information. Okay. It is just holding the information, this table row by row. Row 1, row 2, row 3, row 5, up to n rows. I will be passing the information here. So here information will get passed, and the two-step process will happen when I'm trying to pass it here. So I've just tried to denote here signs, guys, and next slide I'll try to showcase you the entire calculation. So what I'm going to do is, this age will get multiplied by weight W1. This height will get multiplication sign I am writing here. So x2 multiplied by W2. Similarly, x3 will get multiplied by W3, and x4 will get multiplied by W4. All right. So this is will happen, and then what will happen is, after that there will be something called as a summation will happen here. Entire summation sign will be there, summation, and this summation will be nothing but capital X, and capital W. So whatever the signs are there, I'm trying to do now, I will explain you. So what is going to happen in step 1 is, I am going to multiply this inputs by weightages, and that will be summed up here. This is my step 1, and there will be step 2 happening. Step 2 will be something called as activation function will be called upon. This is step 2, and this is my step 1. Step 1 activation function, and whatever this summation is there, summation of X into W will be passed on to the activation function. It will try to give me one kind of output here, O1. And this O1 will be again, guys, passed on to the next layer. So next layer could be here, this hidden layer. Again, the same information, same processing will happen. Again, the step 1 will happen. Again, the step 1 and step 2 will happen. Again, there will be output 2. So here it will generate the output 2, and output 2 will again go through the output layer, and it will give me a final prediction wire, right? So this is what the process is going to happen, guys. So everyone understood? Everyone comfortable? So what is process happening here? So what is the neural network will do? And I am going to write the entire calculation again in the next slide, guys. But until here, are everyone on the same page? I want to understand some couple of confirmation. If you can, guys can give me in the chat box, that will be very nice. So I will move forward for the actual calculation, guys. I'll try to start writing the calculations. All right, Abdul. Thank you very much, Abdul sir. Thank you very much for your confirmation, guys. And couple of more people, if you can give me confirmation, so we can move ahead. All right. Or if you have any doubts, any questions, please ask me here. So this is what is very important. This is the basics. And once we understand them, we can move forward for the further calculation, guys. So please, couple of more people, if you can give me a confirmation, so we can go ahead then. All right. So let me, okay, sir, Kamesh, thank you very much, sir, for the confirmation. So let me revise again what is going to happen. Okay. Okay. Prakash, thank you, sir. Prakash, sir, thank you. Let me revise again what is going to happen here. So what I have decided that I want to predict something called as BMI number. So this is my table look like. BMI number will be my Y column, last column, target. So I am passing my age, I am passing my weight, I am passing my height, I am passing my gender. On basis of this, it will be called as X. This X will be passed on, and it will be put into this formula. Y equal to WX plus B. So W and B is unknown to me. I only have a information of X. And now my entire ANN, artificial neural network, this ANN network has to find out the value of W and find out the value of B. And on the basis of that, it has to perform the prediction of Y, my BMI. Okay. So BMI is my target. So what I did is, in order to perform my prediction, I had created my neural network. This is my artificial neural network, ANN. The ANN has a this kind of a layer architecture. The first layer is input layer here for me. Okay. So first is input layer. This is hidden layer number 1. This is hidden layer number 2. And then I have a something called as output layer here. OP. Okay. So this is my output layer. So what I am passing is, I am passing my age, I am passing my height, passing my weight, passing my gender. So which will be called as X1, X2, X3, X4. And immediately what will happen is, this multiplication is going to happen with the individual weights here, W1, W2, W3, and W4. The multiplication is happening, and after multiplication, it is a summation sign is there. You can see the summation sign of X into W. This is what happening in the hidden layer 1 in every neuron. Okay. So what I am writing here is, step 1 is, actually I am trying to take the inputs, multiply by the weightages, and that will be summed up here. And in step 2, I am doing is, I am passing that entire summation sign of X into W through one activation function. Okay. And once I pass that, it will generate me output 1 at a hidden layer 1 here. Output 1. This output 1 will be passed on to hidden layer 2. It will also generate me output 2. And this output 2 will again multiply by weight. And then in the end, guys, I will get my Y hat, my BMI number. This is what going to happen here. Okay. This way I will receive my BMI. Now we'll try to discover what calculation it will actually do. And let me write it in a clean and phase-wise manner in the next slide. All right. So for that purpose, we'll try to move to this slide, guys. Now what I have done is, I've taken a very single neuron model here, a single information here. And then on the basis of that, we'll try to understand what is happening here. So let's pass our things here again. Age I am passing, height I am passing my weight. And you can call this X4, one more thing out here, which is also going to pass on this to one hidden layer here. And then this will be my output layer. This is my input layer, guys. So what is going to happen? See, when I'm passing this age as X1, height as X2, weight as X3, and this X4 as my, okay, gender G. Okay. So when I'm passing this will be also W4. So what is going to happen? Multiplication is happening, guys. Please try to understand here once again. So what is simply happening is, X1 is getting multiplied by W1. This is what I'm going to write here. So two-step process will be happening here inside this hidden neuron. Okay, hidden layer neuron. Two-step process is happening. Step 1 and step 2. This is what I have written, guys. In step 1, I am just trying to take the summation of individual inputs multiplied by the weights. So let me write that as here Y. So what I am going to write, guys, please try to focus. Let me rub the things once again, and let's try to understand one by one. Okay. So what I'm trying to do here. So first thing is here, I'm taking S1, X1 getting multiplied by W1. Okay, this is what I have written here. X1 multiplied by W1. Then plus, then will be plus sign. Then this X2. I'll try to take X2 multiply by W2. This is what going to happen. This is what I have written here. W2 into X2 plus sign. Then plus, there will be X3 multiplied by W3. And this is what I have written here. W3, X3. All right. So this entire thing, and there will be obviously plus some bias will be there. B. Okay. Plus bias will be there. So what is happening here? The moment I pass, guys, the moment I pass my input, I am going to multiply by the different weightages, which are my thin connection here. Okay. So weights 1, weight 2, weight 3. And this is why I'm calling as Y, guys. All right. So this is my step 1 process is happening. So step 1 process is Y, which is multiplication of input into weights. All right. Once I perform, plus there will be some biases, some constant will be there. And then, guys, in step 2, here, this is my step 2. So same thing I have written here, step 2. So first, what I'm trying to do, when I try to multiply everything here, guys, I'm trying to perform a summation of it, and summation I'll call as Wi. So W stands for all the individual weights, weight 1, weight 2, weight 3. So Wi into Xi. Xi stands for X1, X1, X2, X3. And this is summation, this is happening. So this is what is I have written here Y. And once this summation happens, which is called as Y, guys, that Y will be passed on to my activation function. This is my step 2 Z. Z equal to activation of Y. Correct? So activation of Y will happen. And once this activation of Y is happening, which is here, activation of Y, this is the step 2 here. And once I perform that, it will try to give me output O1 here. Okay. So here out of this neuron, I will receive one output O1, guys. O1, this O1 will get multiplied by this weightages here, O1 multiplied by W4, and this O1 multiplied by W4, which I call as a Z1 here. Z1, same thing I am writing here, Z1 here. Z1 equal to whatever this output I have received. How are weight initialized? Yes, sir. Thanks for asking. Sanam, thanks for asking. I will tell this. I am going to explain you entire weightages processes, that how these weights will be initialized and how these weights will be learned by model. That is called as our optimizer model, gradient descent. I'll speak about it in a couple of minutes. Thanks for asking. Very nice question. Thanks for asking. So I'll write it there. And then what is happening is, guys, where were we? We are here. So one output O1 will be created, and then again it will get multiplied by this W4, which will generate a Z1 actually. So Z1 equal to this O1, we can call O or Z something, O1, which is multiplied by W4, and which is also passed, this Z1 is also passed, guys, here in the output layer also we have an activation function. So this Z1 will be passed on here. So Z1 again passed on in the output layer to the activation function. In the end, guys, in the end, we receive our Y hat here. Y hat. Correct? In the end, we receive here Y hat, and Y hat is my BMI number now. I will receive my BMI number here. So now question, very good question asked by Sanam, sir, ma'am. Okay. So it is very, very nice question that when I am talking about this entire architecture, now everyone is clear what architecture is happening, what kind of entire calculations are happening, step 1, step 2. And this step 1, step 2 process will happen in every neuron, guys. This is just the one single neuron I have taken. There will be multiple such neurons will be there. Similar process will happen and will try to pass on to the output layer, guys. So this entire process is called as forward propagation. This entire process is called as forward propagation. Forward propagation. All right. This is the half job done. This is the half job done for my neural network. All right, guys. So everyone, please give me confirmation if you are able to understand this thing, entire calculation, what is happening here, step by step. I think it is now better calculation. Everyone can visualize what is happening out here and how I receive my BMI number here. All right. So hope you guys understood entire calculation. What is my step 1? What is my step 2? What I am trying to do when I pass the inputs. Let me recap. When I pass the input, guys, I multiply by the weightage, individual weightages, and I try to sum it here. And once the summation is done, that will be passed on to my activation function. So, okay, once that activation function perform, it will generate me the output 1. That output 1 will again get multiplied by this individual weight W, and that whatever Z1 is coming out, that Z1 is also passed by in output layer. It is passed on again, once again, through the activation function, and then we receive our final Y hat, guys. Okay, and this entire process is called as forward propagation. Forward propagation is only half job done, and then something actual learning of the model will start. Actual learning of the entire neural network will start, guys. All right. So can I move ahead now? Everyone understood? Any questions, any doubt as of now? Anything to ask? What is happening here? What is forward propagation? This is the half part, guys. And after that, actual learning of the artificial neural network will start, and that process will be called as backward propagation. All right. So that process is called as backward propagation, and the entire backward propagation process will start. So once guys, just couple of more people, if you can give me confirmation, so we can go ahead and I'll explain you what is going to happen after this prediction. Once I perform this prediction, guys, Y hat, now obviously my job is once this entire prediction is done, all right. So once my prediction is done, once my forward propagation is completed, so what is going to happen is something loss will be calculated actually. So whatever BMI number here I predicted, let's imagine my BMI number prediction is 30 actually, and this is 30 will be compared with the actual one. So I will call as loss. Yi means actual value minus predicted value Y hat. This is the calculation will be happening here. And once I perform this calculation, guys, this will be, let's imagine this is my prediction 30, but my actual is 25. So I'll receive something called as 5 loss of 5. So this loss actually is supposed to get 0, which is getting me 5, right? So which is not correct. And this is where it will try to launch something called as backward propagation. All right, guys. And in the backward propagation only, all these weightages, this weight W1, this weight W2, weight W3, this weight W4, all these weights will get updated. So can anyone now guess that this, when I wrote about the term, guys, when I wrote about the equation, my model equation is equal to Y equal to WX plus B, right? And out of this equation, my x is given to me. X are nothing but x1, x2, x3, age, height, weight, gender, and whatever information I am passing. Right. So if that is given to me and W and B, weights and biases, are unknown to me. So what you can think that, or can anyone tell me that how the entire ANN, how the ANN will be able to start the equation? We'll be able to understand this equation. How to find out initially the value of W and X? Can anyone tell me? Guess. Can anyone guess that what will be the initial values taken for weights and biases, W and B, guys? Because initially I don't have any reference point. I don't know anything. So can anyone tell me how this ANN will try to take the value of W and B, guys, initially? All right, Kamesh. Awesome answer. Awesome, guys. Awesome. Awesome. Dr. Anuja, thank you. Random initialization. Awesome, guys. Awesome. Okay. So this is what going to happen. So, guys, what will happen is initially this W and B will be taken randomly. So they will try to take the random values, and on the basis of the random values, they will try to do a prediction first. Okay, they will try to input random value of W, random value of B, and after random initialization, they will try to calculate this formula, and they will try to calculate y hat. Like this one example you have seen, BMI, we have received something as 30, but my actual BMI is 25. Then I calculate something called as loss. And once my loss is not equal to 0, guys, my backward propagation will start. BP, backward propagation. Okay, backward propagation going to stop. And this backward propagation will use the optimizer, and it will be able to find out the actual value of weights and biases. And this will not happen once. This will happen multiple times. This entire process will happen multiple times. And then after end of this multiple times iteration, we'll actually able to reduce our loss to 0, guys. Reduce our loss to 0. And that entire process will be called as backward propagation now. So let's try to understand what is the backward propagation. Let me rub these things, guys. Now I think everyone is clear what is forward propagation. And before we understand backward propagation, guys, before we understand the backward propagation, I talked about something called as activation function. This ACT, activation function, we talked about something called as my loss function. So we'll try to understand what are my activation function and what are my loss functions. So is there any range to initialize the value randomly as studied somewhere? It is the range. Kamesh, actually what happens is initial when these weights are initialized randomly, they will try to start with very, very small values actually. Yes, whatever information you have seen. So it could be correct, but this is not the exact range actually. Minus 0.52 point. It is not the exact range. What happens is initially they try to take a very, very less values, like maybe starting from 0.0001 to 0.10 or something like that. Okay, so this kind of a range they will start initially actually. So in fact, they will try to start with a very small range actually, very, very small range. It could go up to 1 also, 0.1, 0.15 or 0.05 also. But that 0.05 is very high, like it will not initially go directly for the 0.5. It will try to start with the very initial low rate, 0.1 or something like that. Okay, 0.1. This kind of a random values, very, very small values they will take. Because if they directly start with the very high values, there might be chances that they will miss out some information or they will miss out some steps. All right. So this is what the range they will start. Even very, very low range they will start. So when we go into understand the entire weight updation process, at that time I will explain you guys how the weight updation will happen using the gradient descent, and we'll try to understand the other optimization. All right. So guys, first we should talk about the activation function. We should talk about our loss function, and then we should go towards the optimizers. The optimizers are the one which are helping us to perform the backward propagation and to optimize our loss, and to make our loss close to 0 actually. Let's try to understand, guys. My loss will never be 0. Okay. So if someone says that your loss is 0, that is wrong actually. So that model is not good. That model is bad model, overfitted model. You will never achieve a loss 0. What you can achieve is you are go very close to the 0. You can go close to the 0. You can achieve 95% accuracy, but 5% of the error will still be there. So if you receive something called as 100% accuracy, that means your model is wrong. Simply, your model is overfitted. Your model is overfitted. Let me tell you very honestly that if someone is receiving 100% accuracy, man, that is a bad model. That is a bad model. Entire architecture is very bad. So without God, no one can predict 100% correctly. Even if we go back to our stat rule, what our stat says, guys, if you guys remember what our stat says, in my stats, most of the times my job is to Draw the samples. Draw the samples from the population, random samples. On the basis of the sample mean, which I will call as X bar, I am trying to predict my population mean. I am trying to predict my population mean. And when I have population mean called as a mu, and when I try to create against population mean, means what will happen is population mean cannot be predicted exactly. So that is why we have a concept of confidence interval. So confidence interval says that X bar plus minus this kind of a Z or T score into some standard error will be there. And that is why we'll try to perform a prediction. Okay. So same rule applies here. So yes, Sanam, I will try to take your question now. But if your training accuracy is 100 and but testing is 99, yes, guys, this is overfitting. Yes, this is overfitting. Something is wrong actually. So 100% accuracy means you simply let's try to understand what do you mean by 100% accuracy. Guys, 100% accuracy means what has happened is whatever data you have provided, your model has simply mucked up. Your model has mucked up or try to memorized. It has memorized all the values and simply that values are given back as a prediction y hat. Okay. So it is not doing any learning actually. That is what is called as 100% accuracy. So in order to perform an accuracy, like what will be the cases? Let's try to understand very simply. So if my model receives something around 90% in my training, okay, and in the testing, if it is giving me 95%, this is also a good model, a very, very nice model, because the difference between training and the testing, all right, testing is not much bigger. Okay. So when we try to implement this model now today, so we'll try to understand these things. Okay. But what I should say is when I'm saying overfitting, means my model is giving me accuracy, which is very different from the training actually. In the training, it is giving me something around 98%. And in the test phase, when I'm passing my unknown data, because in training phase, I'm passing my known data. So the pattern is already known to my model. Model is able to understand the pattern. But in the test phase, when I'm giving unknown data, if it is trying to give me 80%, means there is a difference of 18%. So which is a huge gap. So if you receive this kind of a huge gap between the training accuracy and the testing accuracy, means performance not good. Your model failed to generalize the prediction on the unknown data and your model is bad. That is called as overfitting actually. And or something receive you 100% will give you bad accuracy, means this kind of accuracy 100% is overfitting us. So how your model should look like? It should be consistent in training and the testing, and it should not be 100%, because if you receive 100% means it is completely wrong. Something is wrong around the data, right? So guys, let's move forward and try to understand what are my activation function. So activation function, okay. So what we spoke about in the step 2, whenever we try to pass in step 2, this information is passed on, it is passed through the activation function, and this activation function will take this y. Y is nothing but summation of x into w, right? This is what is entire information is all over. So what is my activation function then? Activation function, guys, first let me write the jobs of the activation function. Activation function will perform a triggering function. Trigger means whether to activate or not to activate the neuron. Activate or not to activate means what? Means if this neuron is there and here I'm passing my information, and whatever information summation is happening here plus the bias which I have written here. So whether I should pass that signal, correct? This is what the human brain is doing. Whether to pass that signal to the next layer or not to pass that signal, that decision is also taken by my activation function. So activation function perform the first job of triggering, whether to activate or deactivate, whether to not to activate that neuron. Okay. So that is my job 1, which is performed by my activation function. Then the second job, guys, which I told you, is to bring the non-linearity actually. Non-linearity. Why I'm talking about the non-linearity? Let's try to understand. When you are trying to pass your information, when you're trying to pass the information, this is equal to y equal to mx plus c. This kind of a equation you are passing, or you are simply passing this kind of a tabular data here, rows and columns data. So that is called as linear function. Linear function, because you can fit this entire data into this kind of a parametric equation, y equal to mx plus c. But let's imagine whatever data you have, that data is something called as image data, or something called as a video data, or something called as a text data, actually text data. So that text data cannot be fitted into rows and columns, guys, this kind of rows. So what is going to happen, that we'll understand in our convolution neural network when we try to study the computer vision in our upcoming lecture. So we'll try to understand what is happening, what are these images are there, what are my videos are there. how they are getting converted into something called as a matrices. So there will be 1, 2, 3 matrices will be there, which belongs to the red color, green color, blue color. So that thing cannot be fitted into the rows and columns, and that is why they are non-linear functions. They are non-linear, okay? So that is why we try to bring some kind of a non-linearity using my activation function. This is the second job of my activation function. Second job of activation function. Let me rub these things now so that it will be very, very clear and nice so you guys can understand what is the job. All right. So guys, what I'm trying to say is my job of the activation function here is to trigger the information. Means trigger means activate or deactivate. Second job is to bring the non-linearity because it should be able to handle the image data. It should be able to handle the video data, and it should be able to handle the text data. Right? This is the second job of my activation function. And third job, which is very, very important job, guys. Third job is something called a scaling, transformation. Scaling and transformation. I can call it scaling. Now, what kind of a scaling will be done? What kind of scaling will be done? You will be passing information somewhere between minus infinity to plus infinity. And what will happen is this information will be received by my activation function. And my activation function, guys, it will try to transform that information either in the scale of 0 to 1, 0 to 1, or it will try to perform my entire transformation between the scale of 0, minus, comma, infinity, positive infinity, or it will try to bring my information in the scale of minus 1 to 1, guys. Minus 1 to 1. So this transformation is the job number 3 of my activation function, guys. All right. So everyone understood what is my activation function? Activation function is very important function which will try to perform this kind of a transformation actually. ACT, I am writing as ACT for my activation function, and my activation will perform one of the 3 jobs here, and which is very, very important, which will decide what will be the output generated out of this neuron and what will be the passed on to the next neuron or not. Okay. So triggering information means activate or deactivate that neuron. Whether this neuron will whatever information received here and process, whether I should pass it to the next layer or not. So that information triggering process will be done here. Then bringing the non-linearity, because my ANN, whatever the artificial neural networks are there, that ANN will try to handle not only the linear data, tabular data, also unstructured data, image, video, text, everything, sequential data as well. And then the third job, important job, which my activation function will do, guys, there's a scaling. So you pass input somewhere between minus infinity to plus infinity, it will try to transform that in this kind of a 3 ranges. What are my range? 0 to 1, 0 to infinity, positive infinity, of course, and minus 1 to 1. So this kind of a transformation will be done, and this is what is called as my activation function. So guys, this activation function was introduced by Jeff Hilton actually in 2006, and along with the gradient descent approach. And then after that, still people are trying to work on the different activation function. In reality, there are 20 plus activation functions are available. 20 plus, every activation function has a unique approach, unique functionality. And because of the different situation, because of the difference of the data, because of the different business cases you guys are trying to solve, you have to choose the activation function. Now, next question comes to my mind. I have understood what is my activation function and what the role of this activation function is all about. Then my next question comes up that how I should choose my activation function. Correct? How should I choose my activation function? And do I need to understand all the activation function? The answer is no. Answer is no. You don't have to mug up. You don't have to understand each and every function. What you need to understand is you need to understand certain popular functions. Certain popular activation function, which are around 5 to 6. That is more than enough. And then you can generalize on the basis of this knowledge and based on the situation, which activation function will come and which is will not come and which we to use and which not to use. So next slide, guys. I think everyone is now comfortable. People, Abhay, you were asking for this kind of information that can you please explain in detail like what is the activation function? I guess now you got your answer that what is this activation function, what is the job it will be doing. And now in the next slide, I am going to cover the entire activation function, what are possible list I have included here, guys. So I will rub these things and let's move to the next part now to understand my popular activation function. All right. So this I have covered, guys, my popular activation function. If you want, I will also provide you the resources where you can go through the entire 20 plus activation functions. All right, guys. So meanwhile, I try to drink some water because I am thirsty now. So you can ask me the questions. You can ask me the doubt if you have anything. Or if no question, no doubt, just give me a confirmation to go ahead. All right, guys. So any question, any doubt as of now, please let me know before I go forward and try to understand the entire other things. How to choose activation? Yes, Kamesh. Yes, I am going to cover that now. Yes, I will cover how to choose activation function. I will tell you some loopholes of the activation function, which activation function is good, which one is bad, and based on the situation, I'll teach you how to choose this activation function. Yes, sir. Yes. Anything else, guys? Anything else you want to ask before we proceed? Any other questions, guys? Please ping me. Don't hesitate, guys. You can go ahead and ask any question. There is nothing called as right and wrong. So please express yourself. Try to make it more engaging so we can make it successful. All right. So it's a humble request. Please go ahead, ask question, doubts, queries, and I'll try to simultaneously answer you guys. All right. So guys, let's try to understand this now. Let's try to understand what are my activation function. My simple activation function is verse one linear. So what happening is, guys, linear means simple. What is information I am passing? X input. F of X will be written as same thing. X equal to F of X. Simple linear function. Okay. So whatever information I am getting, whatever number I am getting, I'm just passing that information as it is, or maybe I try to take the derivative. So what is the derivative of X, guys? Everyone know. So I take the derivative F dash of X means 1. Derivative of X is 1. And if I try to take again the derivative next time, it will become 0 actually. So this is only the first order derivative I'll be taking. So I'm just calling my simple function linear function, which will try to do this way. So what it will do is I'm just pass the information, it will try to take the derivative of X, which will be 1. Means whatever information, whatever value you are passing, I'm trying to make it to the 1, guys. Transform to the 1. So this way I can take the value and transform between somewhere minus infinity to plus infinity. So this linear function is mostly used in the input layer only, because in the input layer, I don't have to make any changes. Whatever input I am passing, I have to pass that input as it is, right? So mostly they try to take the linear function mostly in the input layer only. They never use this linear activation function in between layers like hidden layers or output layer. All right. So now this question is answered to you that in linear function will not be used in the hidden layer and not in the output layer, right? So let me rub these things. Let's try to understand our very, very popular function. In deep learning research compulsory, we have to use, yes, sir. In deep learning, wherever you try to develop this kind of a artificial neural network, okay, in artificial neural network, compulsory you have to use the activation function. And activation function will be present in the hidden layer. It will be present in the output layer, and it could be also present in the input layer as well. So everywhere there will be activation function. It is compulsory. You have to use the activation function. All right. So now, guys, let's try to understand our next question. So our next activation function is something called as, guys, sigmoid actually. All right. So sigmoid we guys already know. And last series we have learned something about the logistic regression function. So this logistic regression function, which is used for the classification purpose, when we talked about the sigmoid function. Now what is my sigmoid function, guys? My formula for sigmoid is 1 divided by 1 plus e to the power minus y. So this is my sigmoid function actually. So y is nothing but same thing, y equal to wx plus b. Wx plus b, guys. This is y only. So 1 divided by e to the power minus y. So this kind of a formula is there. So what is going to happen when you pass any y value here? So that y value will be taken and, guys, it will be transformed between the scale of 0 to 1. 0 to 1. This is what the transformation will do. So you try to look at this, guys. You try to look at this one. So if you try to look at this graph of this function, now let's me explain you. This is minus infinity scale, and here between here it is 0, and this is my positive infinity scale. Okay, this is my x-axis, and this is my y-axis actually, the vertical one. And if you try to look at the data, you pass any minus infinity data to positive infinity data, it will try to look at the curve. If the curve shows the S kind of a curve, so you pass in minus data, it will try to bring it to the 0 scale, and you pass any positive data, it will try to transform it up to 1. So this will be 0 to 1, guys. 0 to 1. So that is why this S kind of a shape is created here. So you try to bring any data, and its data will be transformed into the scale of 0 to 1. All right. So this is called as sigmoid function. This is the formula 1 divided by 1 plus e to the power y. Now this sigmoid function is very, very popular, guys. This is mostly used in the hidden layers. Okay. In the hidden layer, they are trying to use it. But there is also some kind of a limitation which we'll speak about, which is called as vanishing gradient problem, which I am going to cover in the upcoming slides. Okay. So this will have a something called as our problem sigmoid function. Sigmoid function worked upon this function is also available in the output layer actually. In the output layer, we try to use the sigmoid function, but this sigmoid function works very well. We have when we have a binary class, two class classification, binary class. When we have only binary class classification problem, at that time only we use the sigmoid function. When we have a multi-class classification where my category are more than two guys, multi-class classification problem is there. At that time, I use something called as sort max function, guys. Sort max function. I'll try to explain what is this sort max function. Sort max function works very well at that time. Okay, something called as sort max. I'll try to write and explain. Okay, first let me explain the other function, then I'll explain, or let's try to understand here only. Okay, so everyone understood what is my sigmoid function. Sigmoid function, the value is, the equation is 1 divided by 1 plus e to the power minus y. Whatever information you pass, this is the graph look like S-shaped curve. You pass the information minus infinity to plus infinity, it will try to transform between 0 to 1. This is what the sigmoid function is all about. Let me rub the things. Now guys, what I told you, this sigmoid function is good for only two categories. When I have a limited category like yes or no, true, fail, or true or false, or pass or fail, or something called as diabetic, non-diabetic, or you can call this as something called as whether this is a dog or cat category. Okay, so this kind of a category, only two category, this is very good. So when I have a multi-class category, let's try to understand. When I have a multi-class category, at that time I will be using something called as my sort max function. Let me write this as sort max function. And what is the formula for this sort max, guys? Let's try to understand. The sort max will be e to the power y divided by summation of I equal to 1 to n, summation of I equal to 1 to, not n actually, it's up to k, I equal to 1 to k, and e to the power y divided by summation of I equal to 1 to k, summation of all e to the power y, all e to the power y. Okay, where this k equal to, or sorry, where this I equal to 1, 2, 3 up to k, guys, up to k. Now what, let's try to understand what is this k actually, and what is this e to the power y divided by e to the power y. What is happening? Why we are calling this sort max function when we have a multi-class category? Okay, so let's try to understand. My rule of the stats, my stats rule says that probability should always be between scale of 0 to 1. And when I try to sum the probability, summation of the probability will be always 1. Okay, this is my rule, stats rule. So let's try to take the example of multi-class classification. Let's imagine that I have passed one information, and this is a kind of a text data actually. I pass my text data and want to understand my sentiments actually. Whether what is the sentiment of the people around this text, okay, when I'm trying to read this text. So then I will have some kind of a category which is called as positive sentiment. Let's take the second sentiment as negative sentiment. And third category I will be taking as a neutral one. People are neutral about these sentiments, okay. So neutral category. So guys, let's imagine what will happen when you try to train your model. Well, let it be a machine learning model, let it be a deep learning model, let it be artificial neural network. You will get something called as probabilities actually. So you get a probability. Let's imagine I received a probability, something called as for positive class 0.7. 0.7 probability. Then for negative class, let's imagine you got the probability as 0.3. 0.3. And for the neutral class, guys, for the neutral class, you receive the probability something called as 0.2 now. So 0.2. Obviously, when I try to do a final classification or final prediction, what I'm going to do is I'll try to take a max of the probability. Max of probability. So what is my maximum probability? 0.7. 0.7 is my max probability. So my final prediction become y hat become my probability 0.7, which is a class of positive class. But now if you try to sum this, let's try to sum this. What is happening here? What if I try to sum 0.7, okay, plus 0.3 plus 0.2? What is the summation coming up? 1.2, which is wrong. What I says, my rule says of the stats that my summation of the probability should be 1, but I am getting 1.2. So this kind of a problem will happen in multi-class classification, and that is why something called as, let me rub these things, my sort max function comes into the picture. Okay, sort max function, guys. Sort max function, I'll try to explain you what this sort max is done. So sort max has this kind of equation, guys, which is says about the e to the power y divided by summation of I equal to 1 to k e to the power y. What is this e to the power y? Now I try to understand. E to the power y, guys, it is a probability of class 1 or probability of an interested class, probability of a class C1 interested. Then what it is trying to do is it will try to take the probability e to the power y above, and then it will try to divide. It will try to divide by summation of all the probabilities. summation of all the other probabilities for the other classes. Other probabilities for the other classes actually. And this kind of a ratio will be created, this ratio. And if you try to create this kind of a ratio and if you try to sum everything, the sum will come to 1, guys. Sum will come to 1, okay? So this is why there is something called a sort match function is there. And compulsorily, whenever you are trying to use a multi-class classification, you have to use something called a sort match function. All right. So something called a sort match function has to be used whenever you try to use a multi-class classification. When you are using a binary class classification, sigmoid function works very well. Linear function you should only use in the input layer, not in the hidden layer, not in the output layer. All right. So guys, let's quickly have a discussion about the other fund, which is very, very popular function which people use various times. When the first initially they develop the artificial neural network, that is called as tan-h function. Tan-h stands for hyperbolic tangent function. Hyperbolic tangent function, tan-h. Okay, what is the formula for tan-h? Let's try to understand. Tan-h says something called as e to the power y. All right, e to the power y minus e to the power minus y divided by e to the power y plus e to the power minus y. So this is the formula where nothing but y equal to nothing but same thing, wx plus b, guys. So this is what the tan-h function is all about. So if you try to look at this graph, guys, this is the graph of tan-h. Now what tan-h says is that by using this kind of a formula, it will try to bring the information between the scale of -1 to 1. And that is why you can see this equation. This is also kind of a S curve, but this S curve is going below the 0 level here. So this 0 level is -1 here, and this is a +1 here. So this kind of a formula is that tan-h e to the power y minus e to the power minus y plus divided by e to the power y plus e to the power minus y. So this is called as hyperbolic tangent function, guys, and it will try to bring the value between -1 to 1. All right. So then second function, guys, second very popular function. Now, guys, people used to use this kind of a tan-h function. It works very well. But let's imagine that whenever you don't want any kind of a negativity out here, because what it is trying to provide, this is trying to provide a negative scale value also and positive scale also. Now, depending on the situation, business situation, if you don't want to use the negative values at that time, you have to avoid the tan-h function. Otherwise, it can also work very well. It can work very well. Now, so what was the problem with the tan-h? It is trying to provide the -1 to 1 range. Now people decided that there will be some situation where I will not require any negative value. Whatever value I will be passing between the scale of minus infinity to plus infinity, I should get only between 0 and positive value. This kind of a transformation should be done. I don't want to deal with the negative values. Now tan-h is giving me something between -1 to 1. So they came up with the new activation function, which was called as now ReLU function. ReLU, ReLU. So ReLU, so guys, ReLU is something called as rectified linear unit. This is the equation I am talking about. Okay, how the graph of the ReLU look like, guys, this way. You can see a flattened curve and then there's a rise in the curve. Okay, so what is this formula? Let's try to understand what is this formula. What is this tan-h function? So this not tan-h, ReLU function. So ReLU has a 3 variants, guys. ReLU has a 3 variant. One is leaky ReLU, one is called as E-ReLU, leaky ReLU, and P-ReLU. P-ReLU. So there is nothing but change. Some small changes are there. I will try to explain and we'll try to move to the next thing, guys. So let's try to understand what is my ReLU function and what is the ReLU function will give you. So how the graph looks like. ReLU function has simply this formula, guys. Max of 0, x actually. 0, x, max of 0, x means what is happening. If you provide any negative value, it will try to give you 0 for that. If you try to provide any negative value, it will give you 0. And if you provide any positive value, it will give you back the same value. Same value will be returned. And that is why if you try to look at the graph, this is a negative scale. So for this negative scales, guys, it will give you something around 0, and whatever positive value, now this is positive content, it will give you back the same value. That is why the graph look like this way. So this is the graph and this is the equation, guys, and this gives you between 0 to infinity, positive infinity value, right? So this is the formula, max of 0, x, guys. Let me write it again. It is a max of this way, max of only the 0, x now, 0, x. All right. So now people understood that there one more addition happened. People argued that, sir, whenever we try to take the negative value, if you try to make them 0, it will try to vanish the effect of the negativeness. So we should give some consideration, some kind of a consideration to the negative value, and that gave a birth to something called as leaky ReLU. So what the formula, max of 0.1, x. Now what will happen for negative value? It will give you 0.1. For positive value, it will give you this, the same value. And this is what the graph look like, somewhat tilt below 0, 0.1. All right. So this is what the max ReLU and max out function is this one. So I'll not go into detail, guys. There are 20 functions. So I have created a list, and this way by the use cases, there's a E-ReLU irrelevant part, try to perform the exponential transformation. You can see e to the power minus y, this is y minus 1 into some alpha, some contribution parameter, some learning parameter they will be take. Learning parameter value will be 0 to 0.1 to 0.00001. This kind of a parameter value they will take, and they will try to multiply this and e to the power y minus 1. Okay. This is what the formula they will try to take, and they try to bring this e value. There will be something called as parametric value also. So parametrically also try to perform a similar kind of a activation or similar kind of a adjustment to the function and to transform the values. All right, guys. So I think this is a pretty much very intense list of the functions, and mostly now coming back to the question how to choose and which one is important. ReLU performs very good. ReLU performs very good. Normal ReLU, not leaky ReLU, not electrical ReLU or exponential ReLU, or not a parametric ReLU. ReLU function is taken very, very popular. Whatever research happened in the artificial neural network, mostly people take the ReLU. Mostly people take the ReLU, guys. ReLU or TANH. These are the favorite function for the people because they works very well. And if you are not interested in the negative value, you should always go for ReLU. And then when you are having something called as binary class classification, you should go for sigmoid. Otherwise, you go for softmax function. And otherwise, in hidden layer, you will try to take the ReLU or you try to take the damage. And in the output function is sigmoid or kind of a softmax, guys. All right. So this is what you should take, and then we'll try to discuss the next step, guys. So let's quickly try to understand the next step now, because we need to understand the entire gradient descent algorithm as well. So guys, you are already aware that what is the loss. Loss means something else as when I pass my input and this is my artificial neural network, it will try to perform everything, and in the end I will get us something called as y hat. And once I get y hat, guys, I will try to calculate my loss function, which is predicted value minus actual value yi, right? This is what is loss. And loss is only for the one data point, actually. One data point. When I try to sum this loss, it will be caused as my cost function, because cost will be for all the data points present in my data set. So this is called as cost, guys. All right. So there are different loss function. We'll try to understand what is my loss. This is my normal loss function. So we'll quickly have a view, guys, because it is self-explanatory. No need to explain much of the loss. Only we'll try to understand this categorical loss, and they will try to cover the other loss function. This is the actual formula. This is something called as mean absolute error. So I am trying to take actual value minus predicted value. Then I can square these values as well. So I'm trying to perform a squaring, and I'm summing up for all the values. And then I'm trying to divide by number of data points. So this is called a mean absolute error. So this is mostly used for the regression purpose, regression kind of algorithms, right? So this is my normal function, which is used in the regression. Then I have something called as my categorical loss function. When I am trying to perform a categorical loss, means I am trying to perform a classes, prediction of the classes, classification purpose, right? See here, sort mass function will be used. This is what we spoke about. But try to understand how the categorical loss function works upon. So what is happening is actually what I am trying to receive is, let's imagine this is my actual value and these are my predicted values. So whenever, let's say I have a multi-class classification out here. So this is will be class 1 probability P1. This is P2, class 2's probability, and so on Pn, class n's probability. So what is happening? Let's try to take example that I am passing some kind of image out here, and within the image people say that there is a dog present, there is a cat present, and there is a human present. There is a human present and there is a car present in the picture. Okay. So this kind of a prediction I'm trying to perform. And this is my reality actually. Y is my reality and this is my prediction of the ANN. Okay. Let's try to understand. If a dog is present in the real, in this picture, there is a dog present out here. So what I will try to write, I write 1. If it is cat present, cat reality in this picture, cat is present, I will write 1. So, but the human is not present, I will say 0. And the car is not present, I will say 0. So in total, I am taking 4 class prediction. Multi-class is 4 classes I am trying to take, and I am trying to predict around these 4 classes. But when I try to perform my prediction, guys, let's what is happening. Let's try to understand. My model says now. My model says dog is present. Yes, dog is present. So I will write 1. Yes, dog is present. Then I am saying whether the cat is present. Actually, in reality, cat is present. My prediction says cat is not present. I am writing 0 now. So human is present. I am saying in reality it is not present. But my prediction says yes, human is present. Instead, now what is happening? Instead of cat, it is saying human is present. And then car is present. Both are agreeing there is not present. I am writing 0, 0. Now the minus the subtraction will happen, guys. Yi minus predicted. This way, I am trying to convert my probability into the some kind of a vector actually. And then my loss calculation will happen in the categorical loss function. And this is 1 minus 1 will be, loss will be 0 because both are same. If this is cat is present, yes, but I am saying 0. So loss is very high. That is loss is equal to 1. And this is also loss equal to 1. And this is loss equal to 0. So I try to sum loss is 2 now. I have to reduce this loss to 0. Right? All right. So this is how it will try to calculate. And this is something called as a categorical cross entropy, binary categorical cross entropy function will be used, and then it will try to use something called a sparse categorical cross entropy function to perform the prediction, guys. Okay, so this is what the different loss functions are there, and I have listed here, guys. You can go back and try to check from here. Okay, so I think everyone is now very well aware what is my loss function, what is my activation function, what are the different function, where to use what function. Now, guys, now is the time to understand how I am performing the back propagation now, and what is my optimizers, and what all the optimizers are present. Let's try to understand in a very simple and phase-wise manner. What do you mean by optimizer now? Guys, we were trying to understand something called as forward propagation here. And in the forward propagation, we understood that I am passing my inputs here to my neurons, and then there will be hidden layers here. Hidden layer will try to perform the hidden layer performance operation, step 1, step 2, and in the output layer, I'll receive my output, right? This is what is the entire process is called as forward propagation, right? Forward propagation, FP, right? So this forward propagation is happening, then we try to calculate something called as loss, which is my loss function, yi minus y hat, and it should be near to 0, close to 0. I'm not writing equal to, close to 0. And if it is not close to 0, means something is wrong, my loss is very high. Then my optimizer, this optimizer will come into the picture, and then the journey will start backward. Backward propagation will start, guys. The backward propagation will start, and in the backward propagation, now is the question will be answered that how these weights are getting found out, and how the entire weight initialization will happen after the random initialization of the weight in the first place. Okay, so this is how the optimizer will come into the picture, guys. And optimizer are nothing but kind of algorithm which will try to adjust the model parameters, which is going to adjust the model parameter in such a way that my loss will become close to 0. My loss will become close to 0. What are my model parameters now? Can anyone tell me? Now I already discussed my model with you in artificial neural network. What is my model of y? And can anyone tell me what do you mean by model parameter quickly, guys? So kind of a check, I want to understand that everyone is on the same page. When I'm trying to say that I am trying to adjust my model parameter using the optimization or optimizer. So when I'm saying model parameter, can anyone tell me what are my model parameters, guys? What do you mean by model parameter? So I have written my equation. Let me write my equation here. Once again, what is my equation in the artificial neural network? Something, yeah, I got answer. I'll try to answer that. Wx plus b. This is my model, right? So when I send Wx plus b, what are my model parameters? I want to understand, guys. No, yi not Praveen Raj. No, sorry, sir. So that is yi is not my model parameter. My model is this way. Y equal to Wx plus b. Wx plus b. This is my model, guys, actually in ANN, right? So in ANN, what are my model parameters? Can anyone tell me? What will be my model parameters, guys? So I want to understand that we are on the same page. And okay, let's have, yes, awesome, Praveen Raj. Yes, W and X, correct, sir. Very Dr. Rambau sir, correct. Weights and biases. Awesome, sir. Awesome. I knew you guys will be able to answer me. Yes, Pushpa, Pandurang sir, weights. Yes, weights. Srinivas Rao sir, yes, correct. You are also correct. Pushpa also. Kesh Pushpa sir, yes, correct. Sanam, no. Sanam sir, not number of layers actually. So it is a correct answer. Mostly everyone has given a correct answer, guys. Thanks for your cooperation and thanks for such a good participation. You guys are really amazing. So you guys are really already scholars. So my job is very simple here. So guys, this is kind of a recap for you. I know I can understand that you guys are already deep into the topics. So when I try to say that my model parameters are this one. W and B, guys. W or B are my model parameters. X is already given to me. And my job out here is to find out the W and B, guys. Weights and biases. And this is what I have to optimize. I have to adjust the value of W and B in such a way that my loss becomes close to 0, guys. And this is what the optimizer is going to do. And let's try to understand what are my optimizer. And let's try to have a recap how the gradient descent algorithm works. Very simple. 2 minutes explanation. We'll try to understand. And we'll try to understand what are my optimizers. So, guys, when I start to talk about the optimizer, very famous optimizer, first and foremost optimizer through which my all the algorithm learns is gradient descent. Something called as gradient descent, right? Gradient descent, guys. So this is first, and this gradient descent is something called as a vanilla flavor actually. So it is a vanilla flavor. This gradient descent has a vanilla flavor. Then there is something called as now a stochastic gradient descent, SGD. And there is a third one. So this is the second one. And the third one is called mini batch. Mini batch gradient descent. Mini batch gradient descent. GD, I'll write GD, mini batch gradient descent. Then guys, we have something called as the fourth one is ADA grade. Then fifth one is ADA delta. The sixth one is Adam, guys. Adam is a very famous and very notorious one. So this is mostly used in most of the research paper. They use something called as Adam. It is one of the best one, very famous, the best optimizer out here, which is using the something called as moment estimation. I'll try to talk about it meanwhile. Within couple of minutes, I am going to come to this Adam and I am going to come to this moment estimation. So something called as momentum. This momentum is also used, one of the variant for the stochastic gradient descent is stochastic gradient descent with, I'll write with momentum. So this is also possible. And then we have a ADA grade, ADA delta, Adam RMS prop, and then Adam and ADA max. All right. So guys, these are my popular optimizer, and everyone's job is to adjust the model parameter. My model is nothing but Wx plus B, where I have an input given to me. So my job is to find out W and B, which I started initially in the random values. All right. So this is what I am going to find out now. So let's try to understand how the gradient descent works. What are my vanilla flavor? What is the difference? I will try to speak about it. Okay. In a one moment of time, within a 1 minute, I'll try to understand. Let's try to understand what is happening here. What is my gradient descent and how it is trying to find out the weights, guys. So let's try to understand. There is something called as my convex function here. So let me draw that convex function here. The convex function look like this one. U shape. U shape. What is the beauty of this convex function? This white point, if you are able to see, this is my actual point. This in the bottom of this convex function, something called as my global minima is there. Global minima. And this global minima, what is the beauty of this global minima? This global minima's coordinates, if you try to check, guys, it is denote to the 0. So now what I'm going to do, how the algorithm is going to work, let's try to understand. I'm calling a 3-dimensional graph here. This dimension is something called as my y-axis. So this dimension out here, which is called as my x-axis, and this dimension out here called my z-axis, guys. So z-axis is here. So let me have a question. So feedback, okay, feedback. Okay, guys, my colleague Chandana has shared feedback link. You can have a feedback link and attendance link. It is both same. You can please mark your attendance and please mark your feedback, guys. Okay. So let's try to understand, guys. So what is going to happen in gradient descent, GD, gradient descent. So I am going to take something called as, guys, my error here, my error or loss. You can say error or you can say my loss on y-axis here. On y-axis, this is my 0 scale here. And then here is my bias actually. Here is my bias and here is my weight, guys. Weight on z-axis here. Okay. So now what is my job? What is my job? Let's try to understand what is my job. My job is, guys, now let me change the scale now. Let me change the color of the scale. Now, guys, my job is to reach. I have to start somewhere here above at a random position because when my equation y equal to wx plus b, I initially started at iteration 1 at a random initialization. Something called as random initialization. So I started here somewhere here in the curve random AK. Here, this is my AK. This is my random W. So this is where I started, and then my entire journey, my entire job is to use this convex function, where in the convex function at the bottom, this bottom point where white point is there, which denotes to my 0 scale. I have to make sure that I have to find this journey. I have to meet this journey. I have to start my journey in such a way that this error or loss is close to 0 here. And at such point, this is called as my 0 point, global minimum point I have to reach. And in such a way that I have to reach through this journey, that my values of the weights and biases are calculated respectively, where my loss becomes 0. Loss becomes 0. And I have to start this journey. And how I start this journey, why it is called as gradient descent, guys? Why it is called as gradient descent is, gradient means I am trying to take the derivative here. I am trying to take the derivative of what? Loss function with respect to derivative of m. And I'm trying to take the derivative loss with respect to C. Sorry, not C, B. Biases. Okay, let me write DL by D M, not M actually. I will write something else B actually. So let me rub this thing. I am trying to talk about my algorithm, which is called as gradient descent here. So in the gradient descent algorithm, what I am trying to perform is, guys, I am trying to take the gradient, which is nothing called as derivative of loss with respect to W and derivative of loss with respect to biases. So this derivative I am taken, this derivative is not the entire derivative. I am trying to take the partial derivative. That is what it is called as gradient now. And descent means whatever this algorithm I am using, this convex function, where I am trying to reach to the 0 point, guys. I have to reach to something called as now the 0 point. This 0 point belongs to my loss. This loss has to be brought to 0 down here. This is zero scale, and for that zero scale, what are my respective value of weights and my biases values? Okay, so for this point, this is what my journey has to be there, right? So this is what it is called as gradient descent, guys, and this is what the entire journey will start. So we'll start with the random initialization, where in the y equal to wx plus b, and let's try to understand what is going to happen, how the entire weight initialization will be done, guys. Initially we understood that we'll try to take the random value. So random point, I will try to consider this one, this as a random point ak. We're going to start, and this is the curve which is used by the gradient descent. And by using this curve in the 3D diagram, because it is a biases one side, weights on the other side, and the loss on the other side, which loss I have to bring it to the zero scale, guys, this loss. Okay, so this is what I have to perform here, and that is why it is called as a 3-dimension here, and in the dimension I have to reach to the scale of 0 here. This error has to be brought to 0, loss has to be brought to 0, guys. All right. Yeah, guys, I will be sharing again. Chandana has already shared this link. I'll be sharing with you guys, all of you. Attendance link and feedback link is same, guys. The same link I am sharing again with everyone. Okay, please try to mark your attendance. All right, guys. So let's try to understand what is happening here. So my entire journey will start here. Something. Let me change my scale color here now. So gradient descent. Why it is called as gradient descent? Descent means coming down. So we are trying to come down, guys, in the curve, and we have to reach to the 0 point. And this 0 point belongs to where error is 0, and that respective value weights and biases have to collect. So what's going to happen? Let's try to understand the journey. We started here on this point at a random point, and I try to input that random value WMB, and then I calculated my loss, guys. Obviously my loss is not equal to 0, and that is where my backward propagation will start. And my backward propagation will try to understand, it will try to go back and try to understand what are the weights and values, and it will try to update, guys. And let me write the values of how the weights will get updated here. The weight new will be updated by using the formula, guys, weight old minus some learning rate eta into, guys, derivative of loss with respect to weight W. So this is the formula using which, guys, my weights will get updated. All right. Okay, Mohammed, it is not possible actually. So yeah, you can speak to Chandana about it. You can chat with her. So she will explain you. Okay. But whatever link is shared, guys, again, let me share the link again in the chat box. So this is the same link, guys. Please, everyone, I request everyone to mark your attendance and feedback. It is the same link. And if you try to miss this link, guys, 60% is mandatory to get the participation certificates. Okay. So it's a kind request that everyone give a feedback and attendance. Okay. It is the same link I have shared with everyone. All right, guys. So let's try to understand. So this is my formula. If I want to update my weight, it will be done by using the new weights will be updated by old weight minus, and this is the learning rate actually, LR, called as the learning rate, which falls in the range of, guys, 0.0001 to something called as 0.10, around this kind of a range. And this, which is very small range, we cannot take very high or low range. So that is why we'll try to understand here what is why we cannot take high and low range, guys. And by using this formula, guys, old weight minus learning rate into derivative of weight loss with respect to weight, I am going to update my weight, this formula. And let's try to understand graphically what is happening. Graphically, I started here, guys, initially random point, and I have taken a random value of weights and biases. I calculated my loss, and I realized that my loss, whatever the value I have taken initially, weights and bias, random value, is not good, because they are not helping you to reach to 0. That is the iteration number 1 will happen. Forward propagation will happen. Then, guys, backward propagation will start now. When backward propagation, I am going to update, go back in the journey. Let's try to understand if this is my entire artificial neural network, and this is my first layer, this is my second layer, hidden layer number 1, hidden layer number 2, and this is my output layer, and this is what it is getting connected to each other. And by this iteration, when we started initially, so let me change the color now. And when we started initially, when we passed out this input layer, this is my hidden layer, and this is my output y hat prediction. And initially I started with the random value weights and biases, and whatever y hat received is not actually equal to the actual value. There is a loss, and then the backward journey will start, guys. Backward propagation will start. In backward propagation, I am going to visit all my neural networks connections one by one. I am going backward until the time I reach to my input layer. And in between, when I am going back, the journey of going back, guys, whatever weights were there, this connection weights are there, all these weights will get updated. This is what is called as backward propagation, and weight updation will be done by this formula, guys. New weight will be equal to old weight minus learning rate into derivative of loss with respect to weights. Okay. So this way, guys, gradient descent will start working. Let's try to understand. It will start initially here. Then what it has to do is it has to take here the slope. This is called as slope here. This will be the negative slope. This will be the positive slope here. Okay. And by using the derivative value, whether it is negative or positive, I have to switch between here to here, guys. Okay. And then my end aim is to reach to this 0 point global minima, where my loss is 0, and that respective value of weights and biases I have to take as my final value. This is my iteration, and by iteration, I have to reach it down. Okay. So what is going to happen? Let's try to understand now. So initially I started to run my neural network, and I realized that end of the date, whatever prediction I've done is not equal to actual value. I got a loss, and my backward propagation will start. In backward propagation, I'm going back, guys, one by one. Sir, when we are using pre-trained model, do we weights changes during the training? No, guys, what is happening is actually whenever we try to take the pre-trained weights, what is happening? We try to freeze our network actually. Certain weights will be freezed on, and then there will be certain layers. Like, let me explain you here. Okay. Very good question. Thanks for asking this one. Sanam, sir, ma'am, Kazi. Thank you very much for asking this question. And let me very quickly answer you this question, and we can start understanding, continue our discussion. Okay. So if you are talking about the pre-trained model, now with this model, we are talking from the scratch actually. From the beginning, we are trying to start this model, right? So but if you are trying to take the model, which is like a pre-trained model, what is going to happen? So this kind of architecture will be there, guys, for the pre-trained model. Let's try to understand. There will be initial layers will be there. So let's understand this one. I am calling one more layer here actually. This is my hidden layer 1, hidden layer 2, and this is my hidden layer 3, and this is my output layer picture. This is the neural network architecture which is connected to each other. Let's try to understand what is going to happen. And in my pre-trained model, okay, in my pre-trained model which we are using, which I am going to cover, guys. I am going to cover the pre-trained model as well in the computer vision. We'll try to take the YOLO NAS pre-trained model, and we'll try to customize this. What is going to happen, guys, here in the pre-trained model? What happens is we'll try to freeze this between layers actually. Let me denote that layer using the brown color now. So this hidden layer will be there, like some model architecture will be there. Within that architecture, some layer will be freezed, guys. Some layer will try to freeze them. Whatever I am trying to show them, this will be freezed actually. And this freezing means this weights will be freezed. This weights will be freezed, and then I am trying to pass my input here, and this weights will be fixed upon. This layer will be fixed, and there will be one flexible layer. Hidden layer 3 will be there. So what will happen is this layer I am not going to change. So this input which you are passing x1, x2, x3 for your own data, that will go through this hidden layer 1, hidden layer 2, and then it will go to hidden layer 3, and then we'll get something called as my y hat actually. And in the backward propagation, guys, in backward propagation, what will happen? My hidden layer number 1 and hidden layer number 2 will be freezed. Those weight will not change. Only the hidden layer number 3, where I'm trying to perform a customization, guys, only those weights will get calculated. Okay, only those weights will change, and then I will go do my backward propagation. I'll try to reach to my entire journey. So that is architecture is called as my pre-trained architecture, where some certain weights of the certain layer will be freezed on, and that is how we try to use the previous knowledge, because that layer will be already trained on the certain data, and on the basis of that, where it is trying to perform this gradient descent algorithm multiple iteration, and it is able to reach to that value of weights and biases. Those weights and biases value will be retained in the layers hidden layer 1 and 2, and that this flexible layer, this layer will also get trained, guys, only. All right, so this is called as pre-trained model. Now, so let me rub these things now, and let us make it very, very clear, and let's try to understand our calculation now, what is going on. So let me recap again what is going to happen here, and what we are trying to understand, and what we're trying to learn here. Okay. So guys, let's try to understand. So this is my formula. New weight will be old weight minus learning rate into derivative of with respect to loss with respect to weights, guys. And this I started here on the initial point, which is very my randomization, and then random thing I try to calculate. My loss is not equal to 0. My backward propagation will start. Now let's imagine what is going to happen. First thing which we'll try to take is it will try to take the derivative of loss with respect to that weights. Now this weight, this derivative will be taken, guys. And based on this derivative, guys, let's try to understand if the derivative value is positive or negative. Based on that, I will try to move from this scale, and then I'll try to understand whether I need to increase my value, whatever the old weight are taken, whether to increase or decrease. Let's try to take example. Let's imagine, guys, this derivative I have to take. Okay, initially I started here at this point. Okay, AK point, and then whatever AK point I had respective coordinates I have taken. Okay, so let's imagine this respective coordinates were in this way. Okay, so this formula I will try to write it here. So I am going to calculate my old weight. Let's imagine old weight was 4, and then minus learning rate. I am trying to take the learning rate as 1. And then, guys, I have to multiply by this value, right? My derivative of loss with respect to weight. Let's imagine if the value of this is positive now. What is going to happen now? If this is positive, guys, so let's imagine this derivative is positive. Let's imagine it has reached to something called as 0.25, positive 0.25, right? This is positive. So what will happen? This is actually old weight minus learning rate into eta, right? So this is same I am writing old weight 4 minus 1 learning rate into my derivative function. So minus into plus will be minus. So if derivative is positive, I have to reduce the value. I have to reduce the value if derivative is positive. If derivative is negative, guys, let's try to understand. So let's imagine the same thing, 0.25, but it is negative. What will happen? Negative minus negative, it will become positive. Means I have to increase the value. I have to increase the value of initial weights. Okay, this is what is going to happen. Let's take the example. If derivative I have calculated with respect to weight and this is 0.25 positive, obviously 1 into 0.25 will be, guys, it will be 0.25. So 4 minus 0.25 will be 3.75. So this will become my new weight, guys. All right. So this will become, yes, guys, I'll try to share again. Juhi ma'am, yes. I'll try to share again the attendance link in the chat box so everyone can again follow up. Okay. I've shared for everyone's reference. So guys, this is how the weights will get calculated and this is what the gradient descent will work. Now, if you try to look what is happening here. So whatever derivative I have taken, that derivative was positive and that derivative I have inputted in this formula. Now my new weight becomes 3.75 means I have to decrease. So this I will try to come here. So this next point, okay. So this is what will happen, and by coming this point one by one, all the derivative will be taken, guys, and I will try to reach to this 0 point this way, and multiple iteration will happen, guys, this way, and this multiple iteration will help you to reach to this one. Now, if you try to take a very high learning rate, what will happen, guys? Let's try to concentrate on this diagram. Let me rub this entire thing and let's try to understand what is going to happen here. So this was the curve. This was the curve, and this is where you started on AK. And if you try to, let me change the color now to the red color. And if you try to take this, and let me write the same formula now. New weight, actually, the new weight equal to old weight minus learning rate into, guys, derivative of loss with respect to weights. This is what is going to happen. And if you try to take this learning rate as 1, and this is old weight, we are taking 4. And this is what the derivative depends upon, whether to increase or decrease, depend on this derivative's value. If it is the derivative value is positive, so we have to decrease the weights. We have to decrease the weights. We have seen, because if I try to input here positive 0.25, right? Positive 0.25 value here. So this minus into positive will become minus. So 4 minus 0.25. This is going to happen, and I am going to reduce my weight to 3.75. And initially, say same thing, guys. If it is I'm trying to take the negative value, so negative minus negative will become plus. I have to increase my value, so which will become in fact 4.25. So I have to increase, guys. So depending on this slope, the derivative which I am taking here, so it will try to increase or decrease, guys. So this way it will try to go here, and in the end, guys, it will try to reach to the 0 point. And once we try to reach to this 0 point where my loss is 0, guys, that respective value of weights and that respective value of biases has to be taken, and that will become my optimal value. That will become, guys, my optimal value is W1 and B. And this way the algorithm will work, guys. All right. So I think everyone understood that this is how the entire process works upon, and this is what the called as gradient descent algorithm. Gradient descent. Now, very quickly, guys, very quickly, like try to understand. We'll try to cover some of the disadvantage of this gradient descent algorithm. Means what will be the problem we will be facing, and last concept we will try to understand, very simple 5-minute concept, which is called as, guys, my dropout layer. And then maybe tomorrow, first thing, we'll try to make a code walkthrough. We'll try to build our own architecture because it's only 15 minutes left. So in 15 minutes, let's say exactly 13 minutes. In 30 minutes, I'll try to consider. I think now everyone try to understand, and I think everyone understood how the gradient descent algorithm works upon, how the backward propagation works upon, and what is your initial, guys. Yeah, guys, it is possible, but it is Rambau sir, Dr. Rambau sir. It is actually possible that you can use this nature inspired optimization, but there is a list of the optimization which I shown you. So research paper says that if you try to use this kind of a research optimization, so they have proved and performed the trial and error. So this is the best way where you can converge, but there is no limitation. Like you can use your own optimization, you can create your own formula and try to experiment, guys. There is no problem with that. Only thing is that you have to perform a multiple iteration and you have to prove that you are trying to bring your loss to 0. All right. So this question is, guys, open-ended, sir. So you can use yes. I will say not no, yes or no. It is an open-ended question. You can use yes, but as long as you are able to prove it. All right. So guys, I think everyone understood how the gradient descent works. how the optimizer works and what is the entire process because of which this model or this ANN try to learn the information and try to bring the loss to the zero. This is called as backward propagation, guys, and this kind of a calculation will be happening. All right. So from administrator, I have received a message from Anand S. Upar sir, Shri Devi ma'am, IT, Mangalore, Karnataka. Thank you very much, sir. So Rumba, thanks. Ellarum, thank you very much, sir. Ellarum Mansile, thank you, Heltine. Somewhat Kannada I can speak, I can understand, sir. I guess from Mangalore you can understand the Kannada. Dhanyavad Galu, sir. Ellarum Anand sir, Anand Upar sir, and Shri Devi ma'am. Thank you. Dhanyavad Galu. Thanks for this kind appreciation, guys. And Prakash Kumar Singh, give me one application related to which concept you are covering. So give me one example related to your concept and we'll try to based on your thing. Yes, sir. Yes, sir. Thank you. Thank you, sir. Thank you, sir. Tumba thanks, sir. Tumba thanks, administrator, sir. Thank you very much. So guys, yes, Prakash sir, I will give you an example. Don't worry, I will going to cover this example. All right, guys. So I can understand my efforts are bear the fruits. You guys are able to understand the grade optimizer. Let's quickly understand what is the difference between the normal gradient descent vanilla formula, vanilla flavor. What is the difference between the mini batch gradient descent, and what is the difference between stochastic gradient descent? And we'll quickly within 1 minute, guys, we'll try to understand what is this momentum concept. Okay. Dharam Kumar sir, thank you, sir. Thank you for your kind words. Okay. So guys, gradient descent vanilla flavor, what happens is, let's imagine it depends on the data set actually. So in order to calculate this y equal to wx plus b, guys, wx plus b values. So this wx plus b value, this calculation is happening using the derivatives of this loss with respect to w. At that time, this derivative taking information, this gradient descent algorithm, when it is working, guys, at that time, whatever data points you have, let's imagine you have a 1000 data points with you and you started performing this neural network. At that time, if you try to take all your 1000 data points at once and then you try to run this algorithm and then you try to calculate your gradient descent, that is called as vanilla flavor, guys. That is called as vanilla flavor. All right. So then when you try to take something called as, guys, mini batch gradient descent, guys, at that time, what is happening? Instead of this n taking all 1000 data point and once, I'm trying to split them in the batches like 200, 200, 200 each. And then I try to find out my gradient descent values like W and B. Okay. So that is called as mini batch. And in stochastic gradient descent, guys, in stochastic gradient descent, I'm taking one data point each, And then I'm trying to find out the value of W and B, guys. So that is the difference. And that is called as entire difference, how the gradient descent vanilla flavor, mini batch, and my stochastic gradient descent works. Okay. So this is the basic difference, guys. All right. Then guys, then third one is called as moment estimation. So what do you mean by moment estimation? Let's try to understand. So in moment estimation, we are trying to bring a time factor here, guys. When we try to calculate the value of W and B, we try to bring something called as time factor. What do you mean by time factor? Try to understand. So whatever the time stamp are there for the latest time stamp, for the latest time, I'll try to give a weightages W, weightages W more, and for the other less weightages, guys. Let's try to take example. If I am trying to predict y is y at let's say December month, December y. Okay. So that time t. So what I am going to do, my December value 23 will depend on something called as y t minus 1, which is November, and then plus y t minus 2, which is October, and so on, right? So at that time, what I'm going to do is I'm going to assign some weightages. For November is my latest time stamp. I'll give a more weightages like this one, 0.6 into then y t minus 1, November value. Then what I'm going to do is, and then after that, my value at December depends on this. December value depends on y t minus 2 now. T minus 2 is October. So for October, I will give a less weightage like 0.3, then multiply by y t minus 2. And then plus, guys, again, the September value, which is also very far away from the December. So I will give very, very less weightages like 0.1 to the September value, which is y t minus 3. So this kind of a weightages are given. Then, guys, we try to perform this entire derivative of W and B finding optimization algorithm. So that concept is called as momentum, guys. And using this kind of a momentum concept, we try to calculate our gradient descent, and using the gradient descent, we try to find out the value of bias and weights, guys. So that is called the concept of momentum. And when we try to use this momentum, guys, that is always advisable. And as per the practice, guys, it is always important that we try to use this kind of a momentum concept always. So that is why in the research paper, you will find the stochastic gradient descent with momentum. So this is the popular optimizer. Then the popular optimizer is Adam, guys. So these are the best two optimizers, right? So everyone understood now what are the best optimizer, how the optimizer works upon, and what is the differences between the others are also having similar experience, but only small formula calculation is different. All right. So guys, let's try to understand the last concept. Okay, something called as now, something called as our chain rule. I will explain, guys, once again tomorrow. So what is the chain rule? It is a small change in the derivative calculation. So chain rule will try to cover. So let's try to understand the small concept, which is a very, very small concept, which is called as vanishing gradient problem, exploding gradient problem, guys. Vanishing, exploding. Let's try to understand what is happening. Vanishing gradient problem is my weightages, whatever weights I am calculating, guys. These weights are getting less actually. Weights are getting very, very less actually. That is called as vanishing gradient problem. And in exploding gradient problem is, guys, my weights, what is W, called as W, my W are getting very large actually. And because of that, guys, because of this weights are getting large, I am facing the problem. I am facing the problem, and that is called as exploding gradient problem. And when I am trying to talk about the vanishing gradient problem, guys, my weights are getting very, very less. Very, very less means close to zero. Close to zero. And because of that, my entire ANN model is not able to learn. Is not able to learn, guys. This not able to learn. This is the problem which has been faced now. Okay, that is called as vanishing gradient problem and exploding gradient. Means try to understand what the name suggests. Vanishing gradient means when I am trying to take the derivative of loss with respect to weight, guys, that derivative becoming very close to the zero, and because of this, my model is not getting able to update my new weights. My weights new are not getting updated, and my almost what happens is one point of time when you are trying to do this iteration, because you will learn that this derivative taking process will happen n number of times until unless we get our loss close to zero, right? At that time, what happens is, let's take the simple example. Let's imagine that we have a value something called as 3x now. So when I try to take the derivative of 3x, guys, first time derivative of this with respect to f of x, right? What is my derivative at the first time? Derivative of x will be 1. So 1 divided by 3 will be 3. So this is the first order derivative. When I try to take the derivative second time, what will happen? This 3 will become k, like constant, and constant derivative 0. So second time it will become 0. So now try to understand what is happening, or let me rub these things, okay? And let me explain you in simple manner. So I initially have something called as like this way. So this value is there, and if I'm trying to take the derivative of f of x, so what will happen? This is x raised to n, right? This is just kind of x raised to n. So what will be the derivative of x raised to n? N into x raised to n minus 1. So this is what is going to happen, means 2 into 3 into x to the power 1. This is what will happen, means 6x. So derivative when I try to take f dash of x, it will become 6x. The next time, if I try to take f dash of x second time, so what will happen? 6x means x derivative will become 1, it will become 6, right? No need to explain this, right? Everyone knows 6x will become 6. And when I try to take the derivative f triple dash of x, at that time it will become 0, guys. Means what is happening? When I progressively taking, when I am progressing, I started with 3x square, and when I am taking derivative first time, second time, and third time, after third time, my derivative becomes 0. Means what is happening here? Same situation is happening here. When I try to perform my derivative taking process, derivative of loss with respect to weights, guys, this derivative after certain epochs, after n number of times, this derivative will become very close to 0, guys. And when this become very close, let's imagine my formula: weights equal to new weights equal to old weights minus learning rate into something called a derivative loss with respect to w. So this, let's try to imagine if my old weight is 4, guys. My old weight is 4, and then learning rate is 1, and if try to become very, very close, and this entire vanishing gradient problem happen because of the sigmoid function as well. Sigmoid activation function, because sigmoid derivative is rise always between 0 to 0.25. And what happened initially, you can, this is the maximum value, minimum value is 0. Let's imagine after taking n time of a derivative become very close to 0, means this sigmoid value, which falls between the range of 0 to 0.25, guys. What will happen if I try to take the same sigmoid function, and if I try to take the derivative 5 times, 6 times, 7 times, obviously it will come very close to 0. Unless imagine if your derivative is like this one, 0.1. What will happen? 0.1 means 4 minus 0.1, which means 3.9. So my old value was 4 and my new value is 3.9, means there is a no change. Very, very small negligent change is there, means your model is not learning anything. Your model is not learning anything which is very significant. So there is a no change in the significant values, And this kind of a problem, guys, this kind of a problem is called as vanishing gradient. And we have taken example. If you try to take the multiple times the derivative of the same thing, that derivative become very close to 0. Because of that, my weights updation will not happen. And if my weights updation won't happen, obviously my prediction will not be good, guys. My loss will not become 0. Will not become 0. That is the problem. That is the problem of vanishing gradient. And same vice versa, and excluding gradient problem. This happened not because of this sigmoid function, because of the gradient. So what will happen in this formula on the new value, which is equal to W old minus into learning rate into derivative of loss with respect to, guys, bias weights. What is going to happen? Let's imagine my old value is -4 and then my learning rate is 1. Now what is happening is the derivative term, guys, it will give you a very large value. Let's try to understand. So here on the graph, you have started at a AK point, random point, okay? And what is happening is you are trying to take the derivative loss with respect to weights. Now what is happening here is, guys, at that time, the derivative which is taken out here, at that time, this derivative value become very large. Let's imagine it become 400. Now I try to input here 400. So 400 into 1 minus 4. What will happen? 4 minus 400, which will become 399. So what is going to happen is my old value was 4. My new value is 399. So what is happening? Look at here on the graph. If I try to start and this talks about the 4, so it will try to go away here, somewhere here. This will be like 399. And when from 399 again, if I try to input value, which will be very different, right? This time, next time after 399, if I try to take the value 399 minus learning rate into some derivative, again the derivative become 500. What will happen? 500 minus 399. What will happen? Around 200 difference. So from here, again it will try to come here, here. This way it will move and it will never reach to this 0 point, guys, where my loss is 0. So that is the problem. This is called as exploding gradient problem. Here my weights are very, very different. Large differences between the weight. And because of this, guys, our entire derivative is not able to converge to the 0 point. So that is the problem of exploding gradient problem, vanishing gradient problem. And in order to, guys, last 1 minute, I won't take your much time. I know it's the time 5 o'clock. I will just take the 2 minutes and I'll try to explain. If this kind of a situation appears, if you try to face this kind of a vanishing problem, exploding problem, and also when we talk about our lecture in some time, then we were talking about something called as overfitting happening, some kind of a underfitting happening. At that time, if I try to reach something called as around 100% accuracy, or my accuracy is not good, I am trying to reach to only 60% or 50% accuracy. At that time, guys, I have to bring something called as regularization parameter or some kind of a regularization technique, guys. Just 2 minutes I'll take. I will not take much of your time. I will try to quickly understand the last topic and I will try to conclude our session. So something called as regularization technique will come into picture, guys. And in ANN, artificial neural network, regularization technique, guys. Regularization technique is something called as dropout layer now. A dropout layer. Now let's try to understand what is this dropout layer. Very, very simple explanation is there, guys. Let's try to understand this dropout layer, okay? So something called as dropout. What do you mean by dropout? Let's try to understand this way, guys. Okay. So what do you mean by dropout? Let's try to understand. So let's imagine this is my neural network, okay? This is my neural network. And initially this is my input layer. This is my hidden layer. And this is my output layer, guys. So these guys, this dropout layer, okay, DL, this value always lies between 0 to 1, guys. 0 to 1. This percentage lies between 0 to 1. Let's imagine if I try to take the percentage as 0.5, my dropout layer value 5. What will happen? Let's try to come here and try to understand. Dropout means what I'm trying to do. I am going to deactivate some of the neurons, guys. I am going to deactivate some of the neurons. And by deactivation, by using this kind of a percentage, I am trying to regularize. I am trying to regularize my entire neural network, guys. This is the concept of the dropout layer. Means I am going to create one kind of a penalty to my my entire ANN. And by using this, I am trying to make it very good, okay? Let's try to understand. If I'm trying to take my dropout as 0.5, means what is happening in the input layer? If there are 3 neurons, right? Out of that, I will try to deactivate 50%. Then, guys, here there are 4 neurons, so I will try to remove the 2 random neurons. I will take and try to deactivate them. And in the output layer, I will have only 1. And this way, I will try to train my first iteration. Guys. In first iteration, I using dropout percentage as 0.5 means half of the neuron will be deactivated, only half will be kept. And this way I will pass my information. This neuron will get activated. The forward propagation will happen, backward propagation will happen. I'll receive my y hat 1. Y hat and iteration 1 will happen. Guys, next time what is going to happen is whatever neurons were deactivated initially, those neurons now will get activated only. And some other neurons which were not deactivated, those will start getting deactivated, vice versa, randomly. So some half were activated, some half were now not activated. That will get activated, and second iteration will happen. You will get something called as y hat 2, and so on. Y hat n will happen, guys. N time of this neural network will happen, and end of it, whatever prediction will happen, I have to combine everything, combine back. I have to activate everything, and then my final prediction will happen, guys. And then my final prediction will happen, and this is called as dropout layer, guys. Dropout layer. Okay. So this is called as dropout, and this is why, guys. And this dropout was very popularized by AlexNet, which was even won the competition at that time. ImageNet competition. This competition happens everywhere, where they try to give you some kind of 1,000 categories of the data, and you have to build a artificial neural network. You have to retrieve a very high accuracy for that. Then only your model will win. By using the dropout, guys, this AlexNet, this kind of a neural network, which was introduced back in 1998, guys, around 2000. When and how to apply? Yes, I will talk about it, Kamesh, in next lecture, because it's already done. I'll talk about it, and I'll try to build a neural network as well. So dropout means we have to deactivate some neuron, and we have to perform the iteration. Again, next time, some random has to be deactivated based on the percentage. Percentage will be between 0 to 1. So you have to choose one percentage, and that percentage of the neuron will be deactivated, and then you will try to perform a prediction, guys. All right. So I guess, guys, today's lecture everyone enjoyed. Hope you guys enjoyed lecture. You were able to understand the entire working of the neural network. So we'll try to focus on certain areas like how to use these neural networks, dropout layers, and then we'll try to talk about it. And then tomorrow we'll try to focus on building these neural networks, okay, with the image data and the structure data. All right, guys. So that's it for the today, and hope you guys enjoyed your entire session. I was able to give you entire query resolution, whatever queries you guys had. All right. So guys, please let me know, did you find the session useful or not? And how did you find the entire session? And for the couple of minutes, we'll try to take question answer, and we'll try to conclude our session for today. And tomorrow we'll try to start with the coding part. That's it from my side, guys. Thank you very much. And let's try to understand. Once again, Chandana has shared a link, guys, feedback link and attendance link. I request everyone to mark your feedback and attendance in the same link. And prior to that, Juhi ma'am also gave me a very nice comment. Juhi ma'am, thank you very much for your feedback. And others, guys, very much thank you. Dharam sir, thank you. And from the admin part, from the Bangalore University, Anand S. Upar and Shri Devi ma'am, thank you very much. Everyone, thank you for your kind comments. So guys, let's have a question answer session for 2 minutes. If you have any questions, any doubts, please ping me here in the chat box, or you can ping your feedbacks as well for today's session. Please let me know. How did you find your session? Any questions, any doubts, please let me know, and we'll try to take your questions, guys. Stage is yours, guys. Please ping me. Why to disable neuron? Guys, to handle the overfitting. To handle the overfitting, you have to disable the neuron. This way, I will explain you in detail. Like if you try to disable some neuron, some of the calculation will be very less, because whatever derivatives are there, because we're going to cover this chain rule. So at that time, we'll understand that taking the derivative of the loss with the weights is not simple. Actually, it is the entire chain. Like whatever weights are there, all that multiple weights has to update it. Then we can update the weights. So because of that reason, we try to disable, which will help to save our calculation. And by this way, your neural network will try to perform better. All right, sir. Prakash, sir. Hope you understood. And I will explain you. Don't worry. Chain rule I will explain once again tomorrow. And then we'll build our neural network. And while building also, we'll try to use this dropout layers. I'll explain in detail with code how to perform. But in short, to answer your question, to save the calculation and to save the model from the overfitting, we have to disable the neurons, so that there will be less derivatives will be taken, and our less chances that our derivative will merge to zero. That vanishing gradient problem will be handled using that disabling of the neurons. All right. So I answer your question, sir. Prakash, sir. Hope you find it correct. Any other question, guys? Yesterday's attendance. Chandana, is it possible? Can we provide yesterday's attendance? I don't think so, right?
No, we can't able to provide that.
Sorry, sir. Srinivasa Rao, sir. Sorry, we cannot provide that link once again, because it was very activated for only one day. Today's attendance we have already shared. Please try to mark it, okay? Please try to mark it. Sorry, we cannot do around anything around it. Then next question comes from Pushpa, K Pushpa. If we disable the neuron, is there any change in the Neural network, entire neural network, right? This is what you are asking. Yes, there will be change. We'll try to explain this. Yes, there will be change. Srinivas sir, thank you. And then what is the different? What is the second question? Rupali S is asking, can we tune hyperparameter tuning like number of neurons? Yes, I will explain this. Thank you very much for asking, Rupali. So there is something called as Keras tuner actually. So Keras tuner is there, and by using that Keras tuner, guys, please try to remember there is a Keras tuner. There is a library called as Keras tuner. By using Keras tuner, thank you very much, Rupali, for asking this question. So by using the Keras tuner, you can hyper tune your parameter like number of neurons, not exactly number of neurons actually, but you can say activation function, hidden layer function, optimizer, learning rate, and batch size. Yes, definitely. So this denotes that Rupali, you are already deep into the topic. Thanks for asking, and this is a very good knowledge for everyone as well. So yes, by using Keras tuner, okay. So please try to remember this name, Keras tuner. If possible, I'll try to show you that tuner also in upcoming session. By Keras tuner, you can perform a hyperparameter tuning, and that is the actual approach. Actually, in the industry, people use the Keras hyperparameter tuner, and by using this, they will try to tune the parameters, guys. All right. So hope, Rupali, I have answered your question. Okay. Prakash is asking, how can you develop a new model based on the ANN related to healthcare domain? Yes, Prakash. Yes, I will share this one. When we try to create a code tomorrow, at that time, I'll try to give you some use cases. Especially, I will try to share this healthcare domains use cases with you. Okay. I'll try to share like if you try to pass one, let's say, kind of a X-ray, okay, X-ray of a chest, then you can looking at the X-ray, you can understand which one is having cancer or which one is not having cancer by using ANN. Okay, lung cancer. Yes, I'll try to share that kind of a lung cancer detection algorithm with you. Okay, I'll not explain everything. It is very simple. We'll make our code walkthrough and I'll try to use case, and with the code I will try to explain with you. All right. So guys, any other questions? Anything else? Nice questions, guys. Thanks for asking. Thank you. Really, thank you. Because you guys are really asking very nice questions. Very nice to hear that. You guys are already deep into the topic. You are able to understand everything. Really nice audience, guys. I really enjoyed talking with you guys and explaining the things. Yeah, guys, please, last 1 minute. Please go ahead and ask if you have any questions, any doubts. I'm sure I have noted from my point. I'll try to use the chain rule and the dropout again when I try to build my entire model tomorrow. And I'll try to use these use cases, guys. Apart from that, guys, anything else? How did you find today's space? Did you find all the calculation I have tried to showcase you in the different slides? And I think my pace was okay, medium, though it was medium, but I think everyone is able to cope up with it. Anything else, guys? Any suggestions? Any queries? Yeah, guys, last 1 minute and we'll try to close the meeting today. It's already late, I know, I can understand. Okay, Pramod Kumar, sir, thank you. Thank you, sir. Thank you for your kind words. Pramod Kumar, good luck, sir. Thank you very much. Yeah, anything else, guys? Quickly, 30 seconds more. Please let me know. Any other doubts, any queries, any suggestions, guys? No, guys, nothing. All right, then, Chandana, I think no more questions for the day. And then we can close this session for the day.
Yeah. Thank you, Vikas.
Yeah,
We'll
thank
wind
you,
up the
guys.
session.
Yeah, thank you, guys. Thank you, everyone. Thank you, Chandana, for your support. And see you then tomorrow, guys.
Yeah.